I'm David Cole, and I'm the president and CEO of the Science History Institute, and I am delighted to welcome you to our December installment of the Joseph Priestley Society and Science and Society Lecture, featuring author and Bryn Mawr College professor, Dr. Michelle Francl. Dr. Francl is going to speak to us tonight about her book, Steeped: The Chemistry of Tea. Her talk will explore the science behind a seemingly very ordinary thing, tea, and she will tell us about the surprising chemistry that actually delivers an elusive goal, the perfect cup of tea. You will doubtless have questions for Dr. Francl, and there will be plenty of time for those questions following her presentation. I should note that for those of you who are joining us in person this evening, refreshments will follow until we close at 8 p.m. That's in the back of our auditorium. And during Q&A, if you have a question, please do raise your hand and one of my colleagues will find you with a microphone. For those of you who are joining online, please contribute your questions via the chat, and we will be happy to share those with Dr. Francl. And for those of you who are joining us virtually, a hearty welcome to you. You represent critical program partners and supporters. And in fact, more than 75% of the people who support Science History Institute actually live outside of Philadelphia and are joining us tonight from locations across this country and indeed from overseas. It's my pleasure to publicly thank you for your generosity in supporting programs like our Joseph Priestley Society lectures through contributions to our annual fund. Our donors help us to continue telling the stories behind the science, as we like to say. If you haven't already had a chance to give to the Institute this year, I invite you to make a contribution at sciencehistory.org/donate, and you can also Venmo us at @scihistory.org. Yes, we're on Venmo. I should also note that there are 3 more virtual Joseph Priestley Society lectures slated for spring 2025. Please check out our website at sciencehistory.org for more information, and I encourage you to save the dates for those 1-hour-long midday JPS virtual programs. On February 13, we will feature a talk on plastic circularity. On March 13, there'll be a presentation on functional foods. And on April 10, the lecture will focus on gene editing and CRISPR technology, all topics very much in the news these days. And we'll be returning to hybrid in-person science and society evening events like the one you're attending tonight on March 19th, 2025, when University of Pennsylvania professor Beth Linker joins us to discuss her new book called Slouch: Posture Panic in Modern America. Are you posture panicking? Well, we'll find out when we come to March, I should say, March 19th. For this evening, there are several people I wish to acknowledge who helped bring this compelling programming to you. In addition to the talented program team who worked on this evening's lecture with Dr. Francl, I want to thank our program partners, the Executive Committee of the Joseph Priestley Society. It is this group of accomplished volunteers who bring their scientific savvy and networks to the JPS programming you've been coming to for 22 years. I would like to invite at this point those executive committee members of the JPS who are in the audience this evening to stand up so that we can acknowledge their efforts. Please do stand up. I know who you are. Thank you all very much. Here's to another 22 years of these programs, wonderful programs. Before introducing Dr. Francl, I want to share one more important piece of news. The Science History Institute will be closing temporarily for a very exciting and extensive multi-level renovation project that includes a full lobby facelift. Take a good look at the current iteration of the lobby. You won't see it quite this same way again. Installation of a brand new exhibition space and the addition of a state-of-the-art digital production studio and a new gift shop. This redesign will improve the public's access to our spaces and expand our programming and our interpretive offerings, both in person and online. So, this means that the last day to visit the Science History Institute Museum before it closes is Saturday, December 21st, of this year, as in like a little over a week from now, Saturday, December 21st. Our museum will reopen on Saturday, March 8th, 2025. But the full scope of the renovation project will not be completed until May of 25, after which time we're planning a little bit of a celebration to which you're all invited. You may read more details about these projects on our website. And now to our featured event, let me tell you just a little bit about our distinguished speaker. Dr. Michelle M. Francl is the Frank B. Mallory Professor of Chemistry at Bryn Mawr College, as well as an appointed adjunct scholar of the Vatican Observatory. She is a quantum chemist who has worked in areas ranging from the development of methods for computational chemistry to the structures of topologically intriguing molecules. Her essays on science, culture, and policy appear regularly in Nature, Chemistry, Slate, and other distinguished publications. She was elected as an American Chemical Society Fellow in 2009 and was the 2019 recipient of the ACS Philadelphia Section Award. It is our privilege to welcome this esteemed professor, scientist, and author to discuss the everyday chemistry that stands behind a universally favored form of caffeinated and non-caffeinated drink, tea. Please join me in welcoming Dr. Michelle Francl.
Okay. Thank you all for coming tonight. It's wonderful to see all these people in the audience, some of whom I know, and many of you, I assume, are tea aficionados. I'm going to ask at the beginning, how many tea-only drinkers do I have out there? Oh, lovely. Welcome. There's no coffee tonight. Did you notice? Only tea. And I'm going to say, if you have not gone to see the wonderful display over on the side about the different teas, I encourage you to do that. All right, to the business at hand, steep the chemistry of tea. So I want to start with where the story begins. And the story actually begins here in this building, not in 1885, but in 2012 when I was a Hertigan Fellow at the Beckman Institute here. And I was using the Othmer Library, which is upstairs. And I was browsing 10 years worth of a journal called Chemical News. And I was not looking for anything about tea. I was looking for things having to do with peer review. But I was wandered in and I found this paper on the infusion of tea. And as a tea drinker, it was very exciting. This is from 1885. It was very exciting because it's written by a woman chemist, Wilhelmina Green. And at that point, it was very rare to see a paper solo authored by a woman. This is an incredibly careful, analytical chemistry exploration of tea infusions. It's among the first that were done. There would not be many more papers for almost 100 years. And the work in here is incredibly beautiful, also incredibly tedious compared to what the modern work is. The pictures of the Othmer Library, and you can, I think, see the Carol I was working at, actually is right here. So there's the actual On the Infusion of Tea book open. We could also say that maybe this has its start in 1976 when I was a freshman majoring in chemistry at the University of California at Irvine. And there is a picture of my general chemistry professor, who is Sherry Rowland, who won the Nobel Prize for the ozone layer, the destruction of the ozone layer by chlorine. And Sherry had a very interesting sort of approach to teaching. And when our first exam came, there were only 4 questions on it, and this was one of them. The color of tea lightens perceptibly when lemon is added. Why? Give all the appropriate chemical equations. I had a moment of panic. This is not what the questions in the book look like. The questions in the book were, calculate the molarity of blah, blah, blah. This, on the other hand, was, like real life chemistry, and I thought, I don't have any idea. And then I thought for a moment and realized that Professor Rowland would not have asked us this question if he didn't think we knew the answer to it. And I realized we've been talking about indicators, and there we went. This is maybe the first time when I felt like a real chemist tackling a problem that was not just a slight change from the problems in the book, but something every day and something that I had experienced, but now I could explain on a molecular level. Or maybe the book had its start in 2020 on Twitter. So this is Twitter. It's January 3rd. It's between semesters, and Andre the chemist, who's someone I know on Twitter. I realize Twitter is gone, but I can't quite bring myself to say the other word. So Chem Twitter, which has now moved to Blue Sky. So if you're a chemist and looking for Chem Twitter, we've moved to Blue Sky. It's great. But the chemistry question for Chem Twitter: is there an extractive advantage to the tetrahedral tea bag over the traditionally shaped one, or does it just look cooler? Well, the first answer for chemists, of course, is anything tetrahedral looks cooler, particularly for organic chemists. So for sure it looks cooler. But I was between semesters, I write this regular column for Nature Chemistry, and I was thinking, I wonder what chemists know about this. Do they know anything about this? And that got me looking at the chemical literature, which I did. It turned out we knew quite a bit. And I popped around for a week or so and wrote an essay, A Chemist's Cup of Tea, advice to chemists from a chemist about how to make a good cup of tea. And then the pandemic happened. So this came out in March, and in March of 2020, we had a pandemic. And Nature sent out to its whole mailing list my essay and said, we're all anxious and upset, and we need a cup of tea. Here's some good advice about how to make it. And an editor read it and said, this is great. Can you turn it into a book? She sends me this email. Like, I have no idea, Helen, that can I go from a 2-page essay to a 200-page book? Unsure, and I'm trying to teach in the middle of a pandemic. So I didn't have much to say to Helen for about 6 weeks, and then she wondered if she'd scared me off. I'm like, no, it's just been a little busy. So she was persistent and said, well, let me send you the book proposal form and see what you can do. Well, it turned out I could do something. So I wrote the book, and to write the book, I not only sat at my computer and worked, but in fact, I did some experiments, and I'm a theorist. So for me to choose to do experiments is very exciting. I hooked things, measured the cooling curves for my teapots. I used constant temperature baths to brew tea. This is my son's wonderful fiance who did all the pictures for the book. So there was a book, and here it is, Steeped the Chemistry of Tea. And it takes us on a journey beginning with the chemistry, then moving to the tea leaves and working our way through what's in the cup, how you prepare it, and finally, what's the technology we use for making it. So on the 24th of January at 6:56 a.m., I got a lovely note from Helen. Dear Michelle, congratulations. The book's been published. And they wanted to let me know how to publicize the book. So share a link, share the good news on your website, do all those things. And I read that and thought, maybe on the weekend I'll get something going. At 7:41, this is less than an hour later, this is out. Today's media reports of an American professor's recipe for the perfect cup of tea. That would be me, the American professor. Adding salt to Britain's national drink is not official United States policy and never will be. And then it goes on, which I'm going to say, I did suggest something about salt, and I will talk about the chemistry of it. But the very last line tells you that they are totally trolling all of Britain. The US Embassy will continue to make tea in the proper way by microwaving it. So this sort of sent things up. So this is my sister. Is this real? I mean, it really can't be real, right? I'm like, Tabby's my niece. Yes, totally, this is real. And my life is blowing up. Then the Prime Minister's office in Britain has something to say about it. Tea can only be made using a kettle. So they're not taking any chances that the American embassy might be joking. They're very clear. You only use a kettle. So this is what happened. These are all the people who were calling and wanted me to call them back, like the New York Times. And in the meantime, I had to teach class. So in the middle of class, my student raises her hand. I said, yes. What question does she have? She says, my mom just texted me and wanted to know, is that your chemistry professor? It is. So here it is. Many things happened. I'm going to say the one that is for me the most fun is I was a limerick on Wait, Wait, Don't Tell Me. So to me, that may have been the peak of my career. It's not any of the papers I published about computational chemistry. It said I'm a limerick on wait, don't tell me. Um, and I will point out that the Daily Mail, which is yeah, I was trying to, I know it's a rag, but I was trying to think of a different word, tabloid. There we go. Somewhat of a tabloid has not only done me once, but now twice, because they talk about grapefruit. So I will talk about both what happens with the salt and the grapefruit and tea. So what do I really want to talk about? What I really want to talk about is tea that's made from Camellia sinensis, which is a single plant, and all of the forms of tea come from this one plant. The Britons thought that, in fact, green tea and black tea came from two different plants, but they did not. They're from a single plant. And the plant is named for George Kamel, who was a botanist in the Philippines in the 17th and early 18th century. He never did anything with camellias or tea, but the whole genus is named for him. The thing he did do is he described these beans, Faba Sancti Ignatii, which are St. Ignatius's beans, and they're a source of strychnine. So it's another alkaloid. There are a lot of alkaloids in tea, and I think that's perhaps the reason that his name gets attached to the camellia. So the big challenge for me in writing this book was try to figure out how to write about the chemistry of tea for chemists, but also for non-chemists. And what would that take to make the book accessible about chemistry to people who had not had a chemistry class, like my sister? So it begins with this chapter, A Cup of Chemistry. And I had to think about how did I take what I know about chemistry and turn it into something that people could not just read, but apply to the everyday things that they see beyond tea. So I really hoped by the end of the book, people would be able to look at the world around them with slightly different eyes and maybe see things a little bit the way chemists do. So what are the four big ideas that I had? So for non-chemists, the four big ideas are all matter is made up of atoms. Atoms are the building block. Opposite charges attract, like charges repel. Materials must get close together to react, which seems pretty obvious. And finally, the one that I tell my students, if this is the one thing they take from my class, I will be happy. Molecular shape is what controls molecular function and molecular properties. It's not the names of molecules, it's not where they come from, it's their molecular structure that control that. But for the chemists need more than that. So for the chemists, there's a little bit of snarky asides. There's some caveats. There's references. So if you want to track down into the literature, you can follow this into the literature. I had a fun talk at Temple School of Pharmacy last week. It was really great to talk to the graduate students who were deeply engaged, some of them, in dealing with chemistry of the catechins. So they were dealing with that. And so they had really deep questions. And for them, the references in the book were the starting point. I'm going to say I'm very proud of this. I'm not going to read it aloud, but this is all you need to know for the whole book, all the chemistry you need to know. And my favorite part, of course, is with no apologies to Shakespeare, here's this very long chemical name. Its other name is sucrose. And chemists don't use these long names very often. We usually use the nicknames, things like sucrose or sugar. And I do that to point out again that it's the structure, not the names of the molecules. Chemists in the audience might catch this line here. Molecules can hand electrons off from one to another, a process called oxidation. What am I missing? Reduction, yeah. But I'm trying not to get too complicated. So just oxidation. So let's start with what happens with the tea leaves. The chemistry begins as soon as the tea leaves are picked. So here's a dozen different kinds of tea which have been produced by different handling once they've been picked. So there's white tea up here. There is tea that's been scented with rose leaves here. Here I think is green snail tea. Here's some tea that's been wrapped in such a way that it will bloom like a flower when you put it into the water. Here is something from PG Tips. So all these teas came from the single plant and they've just been handled differently. So here's a little bit of a flow chart. There's a much nicer version over there, which I will point you to. And it begins when you pick, and then you let things dry a little bit, the withering. And as that happens, enzymatic processes in the leaves begin to take place. And then you want to traumatize the leaves. So you want to deliberately bruise things to take advantage of enzymatic oxidation. I'll show a picture on the next slide. And that's what you get to give you a black tea or oolong teas, some of which are allowed to really oxidize and some only partially. I'm not talking about reduction because it never shows up in here. But obviously, if oxidation is happening, somewhere reduction is happening. You fire teas, and that kills off the enzyme. It's sometimes called killing the green. And that gives you yellow and green teas and pu'erh teas. You dry the teas. You can fire the teas. You can smoke the teas. And to me, one of the most fascinating things is you can ferment tea. And pu'erh teas are deliberately inculcated with a mold and allowed to mold, and that produces an incredibly fine tea. So what about this bruising? So here we have one of these epigallocatechins, and there are polyphenol oxidases, are an enzyme that's in most plants. They're the enzymes that are responsible for producing the bruises in your apples and your bananas. And it's a response to trauma. What the plant is trying to do is take, if something has broken the skin, is to try to trap the oxygen before it can do any more damage. So the oxidases trap the oxygen, and you get this discoloration. And I'm going to say, when I was growing up, my mother was like, it's okay to eat the bruised banana. The bruise will not hurt you. It's okay to eat the bruised apple. But as a 6-year-old, I was uninterested in eating the bruised apple, right? But now I'm very interested in the bruising because this is the same process that produces the beautiful color of these black teas. So it's these polyphenol oxidases, which are changing the epigallocatechins into these theorubicins, which are the pigments, or one of the pigments, that give the beautiful colors to tea. There are other enzymatic reactions going on, and other pigments. So here's beta-carotene and neoxanthin. Beta-carotene gets converted to beta-ionone, the small molecule here, which has a scent of violets, a little woodsy scent to it, that then converts to thiospirone, which is another kind of violety, floral scented thing. Neoxanthin enzymatically gets changed into beta-damascenone, which is a rose scent, but also found in whiskey. So this is kind of the bridge between whiskeys and tea, are some of these enzymatic compounds. Firing the tea leverages the Maillard reaction, which is a way more complicated reaction than what I'm showing here, right? If you know anything about the Maillard reaction, the first thing you're having is like, where's the rest of it all? But in some ways, the base of this reaction is one of these opposites attract. So here's a negative charge on this nitrogen, and here's a slightly positive charge on this carbon, and the two attract each other, and you get a new compound. And in fact, you get lots of new compounds. So some of the compounds you get are things like thiophene and thiazole. These have sulfurs in them, and they have kind of a sulfurous, smoky-ish scent to them that you sometimes detect in tea. You can also make furan, which has kind of a cinnamon taste, a little spicy taste, and acrylamide, which doesn't have any taste. I've highlighted them here in red because both of those are thought to be carcinogens. And this is one thing to realize: this is a natural product. There are a lot of things in nature that are carcinogens, that are not coming from anything artificial. Here is pu'erh tea, where the microbial chemists are at it. And here is a blown up piece of Aspergillus niger, which is black mold, not the black mold you find in some place which has gotten damp. This is the black mold you see on your onions. So if you've picked up an onion, it's got a little bit of dusty black mold on it. This is the mold that's there. And it's named by Pier Michele, who was I think from Pisa, an Italian mycologist. And he named it for the aspergillum, which is something you use to like sprinkle holy water, like to get demons out, sprinkle the holy water. And of course, you can kind of see the resemblance between this and the head of the aspergillum. And he was a priest, so that may explain a little bit why this came to mind for him. So we have all these different ways to produce different chemistries, different chemical compounds in the tea leaves. But what happens now when we want to get those compounds that are in the leaves out? and into our cups. So the very first chapter is about the most important molecule in all of tea, which is caffeine, the drug in the cup. And so I love this piece, which is from Lu Tong's Song of Tea. There are a number of different translations, but the first cup of tea moistens my lips and throat. The second shatters my loneliness. The third causes the wrongs of life to fade gently from my recollection. I haven't quite mastered that one, but I'm working on it. The fourth purifies my soul, but here's the one. The fifth lifts me to the realms of the unwinking gods. And in fact, by 5 cups of tea, I will indeed be unwinking for the rest of the night. The photograph is from a hermit in the mountains of Japan, and that's his teapot sitting in his stove that is built by hand from clay. It's a beautiful spot. I would love to go back. So what about caffeine? The very first thing we need to know about caffeine is the plant does not make caffeine to keep us awake. The plant is not, doesn't care about humans at all. The plant only cares about the plant. And what the caffeine does for the plant is it's a pesticide and an herbicide. So it kills bugs and it deters things from chewing on it. So it's an herbicide. So basically, you know, your cup of coffee or your cup of tea in the morning is a solution of a pesticide. Again, it doesn't matter, you know, about the safety of the thing or whether it appeals to us. It just matters what the structure is and what its function is. And it turns out that this is a little bit of a recycle and a reuse process. So the trash left over from making DNA and RNA or from breaking down DNA and RNA, including adenine and guanine, get converted in the cells in the tea to xanthine, which has got this 6-membered ring and a 5-membered ring, and then this kind of little tail attached to it. And then there's a process that turns this into caffeine. The gene for this has been identified. It's the same gene in tea as it is in coffee. No one has managed to silence the gene, turn the gene off in tea, but they have managed to turn the gene off in coffee. And this is a relatively recent development. So the coffee that's growing with this gene silenced has yet to be mature enough to be harvested. So it's curious what it will taste like minus the caffeine, but it's a natural way, sort of, to decaffeinate things. So, so how does this process work? So the first thing it does is it attaches a methyl group here. It clips off that nice little tail, attaches a methyl group, and puts another methyl group on here, and puts a, whoops, shouldn't do that. There, third methyl group there. So caffeine, another name for it is trimethylxanthine. It was one of the first drugs used for drug doping in cycling. And it was called trimethyl, and that's why it gets its name, because it's trimethylxanthine. So here is one of the receptors in the brain. It's the adenosine A2A receptor. It's a human receptor, but it's found in many others. It's a transmembrane protein. By that, if I drew a line here, this part of the protein would be outside of a cell, and this would be inside of a cell. And here's adenosine, which is what it naturally binds. And it binds it in this little pocket right here. What's shown in the pocket is actually caffeine. And you can see there's some relationship structurally between the caffeine and the adenosine. And caffeine is a molecular bully. So it fits nicely into the space and it just sits in there and hangs out. And when it does, adenosine can't bind. And when adenosine binds, it tells you you're tired and you should take a nap. My oldest son is sitting in the front row. He is on London time because he landed at 4:20, something like that. But he's consuming caffeine in the hopes of keeping the adenosine out of his receptors, because otherwise he'll fall asleep in the front row. I will point out that there's this little gap down here. And if we look at the next slide, there's the gap. Here's the next slide. And here's caffeine. And it's got that 6-membered ring and the 5-membered ring. And the 6-membered ring is the end that slides into the pocket. And it slides into the pocket. And here is PSB36. It doesn't have any other name than that. It also has that same structure, the 2 fused rings. And there it is in the pocket, right? So you see it slides in that 6-membered ring in the pocket. And if I attach a tail to the end of that six-membered ring, it kind of fills that empty space and makes the binding tighter. And this binds 10 times more tightly than caffeine. This is a super caffeine. And like caffeine, it also crosses the blood-brain barrier. When I talked about this in class one day, my students got very excited. They wanted to know, has anyone taken it? Does it keep you awake longer? And actually, I didn't know the answer to that. The paper doesn't say, but I will tell you the reason people are interested in this, it's very rare for things to cross the blood-brain barrier, and in particular for things like Alzheimer's and Parkinson's disease, they're exploring things that do cross the blood-brain barrier, so that's part of it. Grapefruit, I promised I would talk about the grapefruit, and I promised, well, I didn't promise to talk about broccoli, but I will anyway. I discovered that the half-life for caffeine in the body is pretty variable. So some of you may be able to have a cup of coffee or a cup of tea at 6 o'clock at night and have no trouble falling asleep. And some of us will find our way to that realm of the unwinking gods at that point. But it turns out that if you eat a lot of broccoli, Brussels sprouts, those kinds of things in your diet, you can decrease the half-life for caffeine. And so you'll clear it more quickly, and it will have less of an effect on you. Do not stir it into your tea, but add it to your diet. It's good for you. But I brought this up at the dinner table, and my youngest son is getting his PhD in math. He's getting it on Sunday. We're very excited. He said to me, that's not the point. The point is not to clear caffeine more quickly. The point is to like have it hang around, because mathematicians are nature's way of turning caffeine into theorems. It's not my joke, it's somebody else's. But so it turns out that grapefruit will extend the half-life of caffeine. So if you have a glass of grapefruit juice for the next 24 to 72 hours, you can extend the half-life of caffeine. People who take statin drugs probably already know this has to do with an enzyme pathway for cytochrome P450. And that if you take a statin and you drink grapefruit juice, you can raise the blood levels too high. It won't clear itself quickly enough. Same thing with caffeine. There's a number of immunosuppressant drugs that have the same issue. So if you really need that caffeine to hang around, a glass of grapefruit juice will do it. What about the taste of Zen? So what's actually in a cup of tea? There's certainly caffeine, but there are more than 2,000 different compounds that have been identified in tea. And here is a very short list of some of them. So there are the catechins, which are these antioxidants. There's caffeine, there's L-theanine. I'll talk briefly about L-theanine, which is sometimes called the molecule of Zen. It's a calming molecule. There are theaflavins, theorubicins, theobrownins. Some of these are compounds that give rise to the taste. Some of them have to do with pigments and give tea its color. There are a number of different alkaloids in there beyond caffeine, including quinine. You might not know it, but there's fluoride in your tea. And there's a lot of fluoride in your tea. There's aluminum in your tea. There's iron. The iron doesn't do anything for you, alas. There's some uranium. There's a bunch of organic acids, including oxalic acid, which is sometimes linked to the formation of kidney stones. It's also poisonous. It's in rhubarb. My mother told me never eat rhubarb leaves because of the oxalic acid. Little did I know that spinach has more oxalic acid in it than the rhubarb leaves. So if I'd known that as a kid, I could have used that. And there's a lot of insect DNA. So in some samples, up to 400 different kinds of insects' DNA has been observed in tea. It's a natural product. And you would like to see insect DNA in there because it means it has not been overly treated with pesticides or herbicides. So it's actually a good thing to see that. So here was an interesting set of experiments that were done that took to take the taste reconstitution. So they took the compounds that were known to be in tea. This is in Darjeeling tea. They took 51 of them and put them together in the same concentrations that they're found in Darjeeling tea, and then had professional tea tasters taste them to find out, do they taste like tea? And the answer is, perhaps a little surprisingly, yes. It's not a great cup of tea, all right? But it's a fine cup of tea, which reminds me, of course, of, Captain Jean-Luc Picard. who, could just say to the air, tea, Earl Grey hot, and tea would, shimmer into space. And maybe this is how they do it on the Enterprise, right? They put all these molecules together. It turns out you don't need all 51 molecules. This shorter list will give you a decent cup of tea. It's a bunch of glycosylated things and catechins. They are mostly astringent in flavor. You find this out using something called the double tongue test. If you want to know about that, ask me later. There's epigallocatechins in there. There's caffeine in it. Caffeine is a big part of the taste. If you've had decaffeinated teas, you know they taste somewhat watery, and really the part that makes it taste that nice bitter sharp taste is the caffeine. If you take it out, it's not going to taste as good. So I said that there was fluoride in your tea, and there's fluoride at a level of 2.5 milligrams per liter. The EPA warning level is 2 milligrams per liter. And in public water systems, it should not exceed 4 milligrams per liter. So it's way more fluoridated than fluoridated water. The water in Bryn Mawr is not fluoridated, but this is inorganic fluorine. So it's fluorine that's just the fluorine ion or fluorine atom with one extra electron to make it an ion. And there are very few things in nature that secrete fluoride. There is tea, and there's some weird sea sponge that grows off New Zealand, and that's it. Most of the time when fluorine appears in natural products, it's incredibly toxic. So it's organic. So in other words, it's attached to something with carbon, and it is incredibly toxic. And these days, there are a lot of drugs that use fluorine on them to make them more active. And it turns out that if natural product chemists had known about these fluorinated compounds, they would never have tried them for drugs because these things are so toxic. Turns out the drugs are not toxic and they're great. And there's now about 60% of the new drugs on the market include a fluorine atom. This is L-theanine, sometimes called the molecule of Zen. Here I am doing a little bit of Zen in Japan. And this crosses the blood-brain barrier just as caffeine does. It has been shown to be anti-anxiety. So for subclinical anxiety, L-theanine actually will make you feel less anxious. So if you're having an anxious day, a cup of tea is not a bad idea. It also has been shown, at least in mice, to address dyskinesia, which is a side effect of some of the Parkinson's medication. Again, because these things cross the blood-brain barrier, they have some interesting effects. L-theanine is also pretty sweet. If you add some to your tea, I just bought a jar. I realize it sounds like very much like something a chemist would do. I just bought a jar of L-theanine and made it up in different concentrations and spiked my tea to see if I could taste it. If you go back to that list a few slides back with the caffeine and the epigallocatechins in there, one of the things that's not in there is L-theanine. L-theanine does not particularly contribute to the taste of tea. If you start adding some to it, though, it does taste sweet. In green teas, you have a slight umami flavor that comes from the L-theanine, which is different than the black tea that they were reconstituting there before. So if you're having a particularly bad day, I could suggest a good cup of tea. You might also just spike it with a little extra L-theanine. I didn't tell you that. The agony of the leaves. So if you put dried tea leaves into hot water, they writhe. As they reconstitute with water, they unfold, and people call this the agony of the leaves. And so, yeah, so the person who took this picture is sitting in the front row. And is that the day that everything was happening? Maybe. Anyway, I am heating my tea up in the microwave because I am with the Iraqi poet who said that cold tea is worse than death. So I'm not interested in cold tea, and students come to my office and ask questions, and my tea grows cold, and I go down the hall and I warm it up in the microwave. And there's a problem with this, and I'll show you what the problem is. But first, I want to talk a little bit about what you get when you steep tea. The temperature really, really matters. So already in 1885, Wilhelmina Green is showing that at 100 degrees C, at the boiling point of water, you get out all of the caffeine, virtually all of the caffeine, in 5 minutes from loose tea. The caffeine comes out very rapidly before the tannins come out. And here's Spiro and Siddiqui, who are doing this in 1981, almost 100 years later. This is really when the tea chemistry and the literature begin to pick up again after Wilhelmina Green's piece. Here is how long it takes to get the caffeine out. So you can see that very early in the process, you have almost 2/3 of the caffeine out, and that by 5 minutes, you're at almost 100% of the caffeine. So caffeine is the very first thing that comes out, but it's very temperature dependent. Oops. So at 60 degrees Celsius, you get like half of the caffeine. So if you've been to a conference where they have, the little things with sort of lukewarm water in them, they're depriving you of your caffeine. Complain. Yeah, definitely complain. You really need to get that water above 90 degrees C to really get out as much caffeine as you might want. So this is XKCD, which is a cartoon. This is yesterday's cartoon. So we're back in the way. And ways of making tea. I will point out that you do not make tea in a kettle. You use the kettle to make the hot water. And you boil water not in the pot, you steep it in the pot or in a mug. And of course, microwaving it is definitely not the way to do it. And I think that if you microwave the tea bag separately, you can set it on fire, but did not try that at home. So here is my microwaved tea, and you might see that there's a little bit of a kind of film on top. That film is called tea scum. And it's a floating raft of antioxidants, of catechins, along with ions, so magnesium ions and calcium ions, which have a +2 charge. And the bigger the charge, the more attractive they are. So these things latch on, especially in hard water. There's a nice letter over there about reproducing the water to get the right kind of, presumably tea, for the visiting king and queen. So this is a raft of antioxidants that's floating there. A lot of the flavor compounds are also tied up in that. So your tea, if you microwave it, is less flavorful. And here I've reheated the tea, but if you have noticed when you make tea just by boiling your water in the microwave, it comes to a boil so fast that you don't get out a lot of carbonate. There's carbonate in here too. You don't get out a lot of the carbon dioxide, so you end up with more carbonates in there, more tea scum. So if you make this in a microwave, it's really not the best cup of tea. I understand there's lots of reasons to make it in a microwave, and as you note, I've been caught, right? And you can get rid of the tea scum in the same way that you get rid of scum in the bathtub. You use a chelating agent. So citric acid will work great. Yeah, no, so that's why a little lemon in the tea will take care of the scum. Okay, sugar and spice. This is bergamot. It's citrus that grows in Italy, and its oils from its skin are used to scent Earl Grey tea. And it's thought, no one really knows what the origin of this choice to scent it with this is. Some people think that it was done because linalool, this molecule here, which is found in bergamot, is something it's one of the aromatic scents that you smell in tea. And if tea gets old, you lose some of the scents, and they think maybe they were taking low quality or old tea and kind of like masking that by adding the bergamot, which had the linalool in it. I'm gonna say I don't like Earl Grey tea very much. I live with someone who likes Earl Grey tea. I did a thing with the Royal Society of Chemistry and someone from the Great British Baking Show, who is a chemist, who was trying to convince me to like Earl Grey tea. He baked me a whole cake with everything Earl Grey. It was great. I still don't like Earl Grey tea. But this molecule is in large proportion what you're smelling in Earl Grey tea, but it is in regular tea. And the interesting thing about this molecule is it's also something that's been shown to reduce anxiety and also to reduce pain. So they've done experiments with mice, and if you give them lanolol, they end up having a decreased response to pain. And if you give them Narcan that blocks the opioid receptors, then that also blocks lanolol. So this is somehow playing into the same things that the opioids are playing into. So if you want a cup of tea that's going to make you very chill, Earl Grey actually is the way to go. And so the person in the front row is right. He's grinning at me. What about milk? If I talk about tea in Britain, people are always like, milk first, milk second, what's the deal? It turns out there's an international standard for making tea. This is excerpted from the International Standard for Making Tea. It's not the standard for drinking, it's the standard for quality testing. And so if you look earlier on, they use a lot of tea. It's pretty concentrated. But here they essentially say, well, pour it into the bowl after the milk. So they're all about milk first. But they also say, yeah, you can do it afterwards too. It doesn't really matter. You do need to worry about the temperature range of things because it might curdle. I said something about that in an interview, and that upset the Britons too. Warm milk, never curdles. I don't know. I don't put milk on my tea. But I'd like to highlight something else about this, which is this is Muriel Bristol, who was a biochemist, and she was having tea with two friends, another biochemist she eventually married, and a mathematician. And she said she could tell the difference whether the milk was added first or second. And the guys were like, yeah, no. And she's like, test me. And they're like, okay. And the mathematician was trying to think of a test where he could tell if she was just guessing. And if you do things with stats, you might know about the null hypothesis. This is where the null hypothesis came from. This is the paper by Ronald Fisher. That was the mathematician she was having tea with. Mathematics of a lady tasting tea. So we get the null hypothesis really from this question about milk first or second. So it's a very important question in some ways. And indeed, it turns out Muriel could tell the difference. So she was right. And we get a little bit of stats from that. Ways of making tea, how angry British people get. They didn't put this on probably because it would have to be kind of like way over there. Adding salt. So I suggested that if your tea was too bitter, like if you let it over brew, adding a little bit of salt can help ameliorate the bitterness. And this is, I'm going to say, half a page in a 200-page book. And I'm mostly proud of it because it was really hard to track down the literature about this. It was really tough. And I was tracking down the literature because in an 8th century manuscript, and in fact, on the table over there, there's the book that this comes from. At the first boil, add a suitable measure of salt as seasoning according to the amount of water. Do not make the water too salty, otherwise the flavor will be salty. And this is the 8th century, and I'm trying to figure out why. And of course, this is the outrageous tea recipe, right? But this is not my tea recipe. This is a recipe from a tea master in the 8th century in China. And in fact, there are a lot of tea recipes that call for adding a little bit of salt. And it turns out what it does in many of these recipes is indeed block the bitterness. Sodium ions will do that. Zinc ions will do that. They're not blocking a receptor per se, but they block the perception of bitterness. And there are people who discovered this are the coffee chemists. And there's some couple beautiful papers that describe the molecular interactions that you get with this. And so I was very proud of having tracked this down. So that's one of the things I told the reporter, and that's what did it. So it's good for sales of the book, I'm going to say. But that's the bit about tea and salt. The last thing is maybe you've noticed I have not answered the question that the book started with, is does the shape of the tea bag have anything to do with what the tea tastes like? And the answer is no. And in fact, somebody has done it, right? So here's the paper from 2001 where people looked at the shapes of tea bags. The shape of the tea bag is immaterial, only the size matters. And this has to do with one of those big ideas of chemistry, proximity. If the tea bag is too small, the tea in the inside does not get well exposed to the water, to the solvent, not enough proximity, and so you don't get extraction that's as good as you would get if you had more room. These tetrahedral tea bags, this is PG Tips, sourced from England. The which is no longer made. Like in the last year, they stopped making the tetrahedral tea bags. But you can kind of see this has more extra space in it than does the little pillow. These kind of flow-through tea bags have like double the size. So it's really all about the size and not about the shape. But because it's about the size, and if you think about getting good exposure to the solvent, maybe you don't want it in a bag at all. And in fact, what you want to do is use loose tea. And I really advocate in the book for using loose tea. You give many more choices, and you're not losing any of the scent to the filter paper that's the tea bags are often made of. So here is a set of tea infusers from my collection. They range from the whimsical, oops, where's the whimsical? There's the whimsical little, the little yellow submarine. There's this one that you can tell I've used a lot, right? There's a very prosaic one from OXO. There's one for the owl for Bryn Mawr. This one comes from the Metropolitan Museum of Art, right? Very, very snazzy. Turns out that you need a pretty big infuser to allow the tea leaves to fully brew. They expand by a factor of 4 to 5. And you might wonder why I'm showing you a picture of a telescope and a astronomer sitting there. And I'm showing you that because I went to measure the volumes of these so I could predict how much tea you could make from them. But typically when you measure the volume of something, you pour water or another liquid into it. And of course, what's the problem with that? These things all deliberately have holes in them, right? So you cannot measure their volume that way. You could do a little math if you wanted to, but some of these, like the yellow submarine, are pretty odd shapes. So what do? Well, it turns out that the astrochemists who were trying to measure the density of meteorites, something they did not want to put their meteorites in water or in oil. How do you figure out the density of these things? Well, you need the volume. You use sugar or small glass beads. And they use small glass beads to measure the volumes of things. And in fact, there's a lovely paper, if you're interested in the density and porosity of meteorites, I can recommend this, by Guy Consolmagno. That was the guy on the previous page, and Dan Britt, who's from University of Florida, I think. So here's a bunch of infusers. Here's their interior volume measured using the methods in this paper. Here's how much dry tea you should be able to put in, and here's the volume of prepared tea you can make. The little fancy tea stick from the Met is terrible, right? I can make 3 milliliters of tea. That is just not worth it. On the other hand, that OXO basket or the nylon basket, I can make a good pot of tea from those, and that's terrific. The yellow submarine is also not great and is a real pain to clean. So when I do this, I want to use as big a basket as I can use. The last bit is about what kind of teapot do you use? And this has to do with how you keep the temperature up while you brew it. This teapot here, I bought in Kyoto in Japan. And I bought it on a trip where we were visiting various hermits up in the mountains. We had everything in our backs. We were carrying backpacks. And I bought this like day 2 of the trip and then carried it around Japan. So I deeply am invested in this teapot. It turns out it's not so good, and I'll show you why in the next slide. This is kind of a regular ceramic teapot. This teapot has got an unglazed interior, and you pick one tea to use with this, and you let it kind of build up a patina inside. This one has its own built-in tea cozy. This is the very best teapot ever. It is not a teapot, it's a coffee pot, and you may be able to see it's double glass walled. So it really keeps the temperature because you have this insulating extra layer in here. And this is my very best teapot, and as I said, it's a coffee pot. Let me show you why my other teapot is so bad. So here is a pre-warmed, this is the cooling curve, and this is my cast iron teapot. I've pre-warmed it, and at the very beginning, like less than or just roughly a minute in, it's already down to 92, 93 degrees. And well before the tea is brewed, it has dropped below the ideal steeping temperature of 90 degrees C. This is a terrible pot to use to make black tea, sad to say. It's good for green tea. You do those at lower temperatures. So it's not a complete loss, but it did make me sad because I was not getting the best cup of tea. If you really want the very best cup of tea, you might use a constant temperature bath. And this is a constant temperature bath. And I do this, there's film of me doing this in my kitchen. I will tell you that I do not normally do that, but it does make a terrific cup of, terrific cup of tea. So what about the perfect cup of tea? If you are looking for caffeine in your tea, you want high temperatures. Antioxidants, let it go for a longer time and make sure to agitate it, like bounce the tea bag up and down or wriggle the infuser. If you need a calming cup, L-theanine is your key. That increases with longer times. Although you need, like, if you want the maximum L-theanine, you have to brew it for 90 minutes, at which point it is seriously undrinkable, salt or no salt. Again, I tried it, I promise. Or you might choose Earl Grey. You should pre-warm the pot or mug to help keep the temperature up. These things have beautiful scents. Scents are volatile. They come in the gas phase. Take the lid off of your cup. Yes, you're going to spill it maybe, but take the lid off. Use loose leaves and a large infuser. And again, if you've let it go too long, a little bit of salt will not hurt. After all the fuss in Britain, when there was a black tea shortage, the newspaper recommended strategies for conserving your tea, one of which was if you overbrew it, don't dump it out, add a little bit of salt. So I felt very vindicated. But the best cup of tea is the cup of tea that you enjoy, and the book tries to tell you how to tweak how you make it to get out what you really want. So I would like to say thank you to all of the people who supported me in doing this, the Royal Society and Helen for bugging me until I did it, Bryn Mawr, who supported me for almost 40 years as a faculty member, the Specola Vaticana, which is the only place I drink coffee, but who nevertheless have cheered me on as I wrote the book. There's a great picture of me holding the book with a cup of coffee in my hand. The Klaus Fund for Science and Public Policy, the Mallory Professorship, the National Science Foundation, which funded some of the initial work about weird things in tea. Some of my editors, Stuart Cantrell and Gavin Armstrong from the Nature Chemistry Group, Sabrina Vorvilius, Laura Helmuth, who was at Slate and encouraged me to be snarky when I wrote, and helped me develop my voice. And then various colleagues and my students who asked lots of interesting questions, and my family who listened to lots of stuff about tea for probably longer than they wanted to. And I thank all of you for your attention.
So that was terrific. Sounds like more grapefruit in my breakfast tomorrow morning is in order. Undoubtedly, you have questions. I know online we're going to be gathering a few questions. So if you're online, please do feed your questions in the chat. Happy to take a couple of those, but I'm sure we have questions in the room. My colleagues will be circulating with the microphone, and perhaps we'll start where you are, Lisa, and go from there.
You discussed the effect of grapefruit. Is that just particular to grapefruit, or is it general for all citrus?
It seems to be particular to grapefruit. Yeah, so Lisa's got the microphone, so I'm going to let her kind of control the questions.
So I lived in Asia, and when we cooked broccoli, we put soy sauce in the water to make it taste less bitter. Is that the same chemistry?
Yes, yes, it is the same chemistry. Anything that's too bitter, the salt will do that. Yep.
Could you elaborate a little bit on the lid off? You want it brewing with the lid off, or what's,
Once you've brewed it.
once you've brewed it? Okay.
Yeah, once you've brewed it.
Thank you.
Most people want to take the lid off when you brew it because otherwise I think it traps too much of I'm not quite sure too much of what it traps, but it traps things and you really don't want them in there. So.
You said to ask about the double tongue test. Can you elaborate on that?
I sure can. It's a test for astringency. So we're kind of, in Philadelphia, there's the Monell Chemical Senses Center, which does a lot of incredible work on, looking at flavors and how we perceive them. But the double tongue test is you take a sample of what you want to determine the astringency of, and you take plain water, you put plain water on one side of the tongue, and you put the astringent compound on the other, and then you stick your tongue in and out of your mouth rapidly for 30 seconds. And a trained tester can then tell something about the astringency of the one on that side. I'm not a trained tester, so I can't really tell you anything. And I tried it finally. It took me a long time to try it because it's hard not to laugh while I did it. And I really can't tell much of a difference between one side or the other. But again, people who are trained tasters know what they're doing. Yeah. See who's got Lisa has the mic. There we go.
Yeah. Thank you so much for all of this. So I just want to ask, because I'm Persian, the way we make tea is different. We have a double kettle, like
Yep.
the teapot, there's the steam. And for me, just like just brewing the tea in the teapot, just with the tea leaves is not that tasty. It definitely should be steamed with the boiling water, so I get the taste of it. I don't know why is that, just it's to me different. I don't know how it does it with the chemistry. So if you know anything about that, I would really be happy to know about it.
I know a little bit because you're getting higher temperatures with the steam. And so that gives you a different set of compounds that you get out. There are a number of different ways to make tea. I talked about tea infusions, right, where you're soaking the leaves. You can do decoctions, which is like chai is often a decoction where you boil the leaves in either milk or in water. And that gives you a different set of compounds. The way to make it in Turkey or in Persia by steaming it gives you a higher temperature, and that gives you a different set. If you make it in a K-cup, I'm not advocating, right? I'm just describing. If you make it in a K-cup, that's perfusion. You're just getting it through. And each of these gives you different flavors because you're getting different compounds out. And there's not much, most of the work is done on the infusion of tea, which is why that's mostly what I talked about. There's not much work done on the other methods of making tea in terms of what specific chemical compounds you're seeing.
Question online?
Should filtered water be used?
If you want to avoid the formation of scum, yes, because the filtered water will have, if you're filtering it to get the ions out, that will make a big difference. Some water has like a bit of chlorine-y taste, and that will also not mix well with your tea. So yes, you'll get a better cup and a more consistent cup with filtered water. The water at the college is so hard that I can tell the difference between the tea I make at home and the tea I make at the college. But the color is different even. And someone
Hi.
over there?
Oh, there we go. Little guy. Kind of piggybacking off the Persian woman here. Did you look at anything with how the East Africans make their tea with boiling it in milk and how that affects some of the extraction of the alkaloids and stuff?
I did mostly with respect to Indian tea where they boil it in milk. And to look at some of the compounds there, but there's also spices involved. And so mostly I looked at the spices because there's some chemistry involved with the spices as well as the tea. And there's a literature on it, but I didn't find any literature just on the tea itself. So I really don't know much. I could write a whole nother book.
Hi. Oh.
It's hard for me to see where, there we go.
Back here.
Okay.
I fill my electric tea kettle in the morning and use the water, boil it again and again until it's gone. Does that make a difference in the flavor?
Yeah, you're driving out a lot of the oxygen. If you drive out too much oxygen, if you drive out too much carbon dioxide, the tea can taste kind of flat. And part of it is if you drive off too much carbon dioxide, you're driving off too much of the carbonates, which can give you that kind of sharp taste. You may not notice it. Some people will notice a kind of flat taste to it. But if that's what you've done for a long time, you probably don't notice. And that's okay.
We have time for one more question, and I've got it right here.
Good evening, thank you. Question regarding any insights you have on how the pH of the water affects the taste, whether the acidity or alkalinity affects taste.
Actually, I don't know. Partly because generally the water that's used is at a pH of 7. So if you look in the literature, people are controlling the pH. And I don't know of any exploration of what happens when you make it more acidic or more alkaline. But that's a really good question. And if you send me an email, I'll see if I can, dig out the answer.
Amazing presentation, and thank you once again for being here tonight. Good night.